So today we're going to talk about assignment number 2. So assignment number 2 is on multi-threading. The concepts are multi-threading and synchronization. So we will be creating multiple threads to do something in parallel, and then we will be synchronizing these threads using multiple methods. Okay, so the idea in this assignment is to generate a large array of data, and that array has random numbers, but these random numbers are non-negative. And the program will be searching for the minimum, finding the minimum. Of course, finding minimum in an array is a trivial problem. It's not a hard problem. So you just scan the array and keep track of the minimum. Now here in this assignment, the point is to do this in a multi-threaded way, in parallel. Create multiple threads to do the search in parallel. So for example, if the number of threads is, let's call it k, if it equals 4, by the way, the number of threads is going to be a command line argument for the program. So the program takes a number of command line arguments. One of them is the number of threads. So the first command line argument is the array size. The second command line argument is the number of threads. The third command line argument is the index for the 0, where to put the 0 in the array. And we'll see what the point is. So if k is 4, we will divide this array into 4 divisions. Let's take as an example, if the array size is 100. Of course, in the assignment, we will be using larger numbers. But in this example, let's assume that the array has the array size n equals 100. So in this case, we will have 4 divisions. Division 0, division 1, division 2, and division 3. And division 0 is going to start from index 0 to index 24. Division 1 is going to start from index 25 to index 49. This will start from 50 to 74. And this will start from 75 and will end at 99. Okay. So one of the functions that you will need to write here is the compute indices or calculate indices function that will take the array size and the number of threads, and it will fill in a 2-dimensional array of indices to reflect a division like this. So the indices array in this case is going to be like indices is going to have a row for each division. So there is a row for each division, and there are 3 columns. First column is the thread number. Second column is the start. Third column is the end. So in this example, the indices array will have 4 rows and 3 columns. Well, the number of columns is going to be 3, no matter what the size is and no matter what the number of threads is. So the number of columns is going to be 3. The number of rows is going to be equal to the number of threads. In this case, it's going to be thread 0 that starts at 0 and ends at 24. Thread 1 starts at 25 and ends at 49. Thread 2 starts at 50 and ends at 74. And thread number 3 that starts at 75 and ends at 99. So you need to write some code that will do this division. It will divide the array like this.
When the array is an odd size, or where there's like a remainder, I ended up I was messing around with that part. I just made the last one a little bit bigger than the others. Is that going to be okay?
Yeah, well, it doesn't matter. In fact,
Okay.
we will not test it on odd-sized arrays because it's, all the sizes are going to be even. Well, your code should be able to handle odd-numbered or odd-sized arrays anyway, but we will not test it on odd-sized, and it doesn't matter. One plus or minus one entry is not going to make a difference because the whole point here is to do the search in 4 different methods and to do the timing. Now, and the actual array sizes that we will be using to test your program on are going to be 100 megabytes or 100 million elements. So with 100 million, it doesn't matter if one of the divisions has an extra item. Okay, so plus or minus 1 is not going to make a difference. Okay. All right. So the point here is to fill in this with random numbers, but if there is an index for the 0, so if index for 0, if index for 0 here is 53, then put a 0 at 53. If index for 0 is 71, then put a 0 at 71. So you put a 0, after you generate random numbers, you put a 0 at the specified index, the index in the command line argument. And of course, as we explained the assignment, it will become clear what the point in putting a 0 is. If the index for 0 is minus 1, don't put a 0. So the array will not have a 0. If this command line argument, the third command line argument is minus 1, then don't put a 0 in the array. So there is the data generation phase in the program. You generate the data according to these rules. Then you search for the minimum using 4 different methods. And you do the timing for each method, and the program has the timing code is provided to you. So the code that does the timing for each method is provided, and even the code that prints the time for each method. Now, what's the point here? Well, what's the point in putting a 0? Does anyone see the point in sometimes we put a 0, sometimes we don't put a 0?
To check the minimum. 0 is the minimum.
Yeah, we're checking for the minimum, but when there is a 0, how does that affect the search for the minimum? Yeah.
It's going to always be at that index, so you can test to make sure that we're in which thread you want to put it in.
Okay, so if there is a 0, then we know that if we find a 0, the 0 is necessarily the minimum because we know that the numbers are non-negative. So the point here is that as soon as we find a 0, the search is done. Okay, we are done. So in the sequential, so let's see what the 4 methods are. We have 4 methods. Number 1 is sequential. Number 2 is parent waits for all children. Number 3 is parent checks on children. Number 4, parent waits on a semaphore. Okay, so sequential is easy. Sequential, you just do the sequential search for a minimum. But if you find a 0, you should terminate as soon as you find a 0. Okay, so that's the sequential. Now, parent waits for all children. What are the children? The children are the threads. So when the number of divisions is 4, the parent is going to create 4 threads using pthread create. So the parent is going to be in a loop for I equals 0, I less than k, I plus plus, pthread create. It will create k threads. Then after it creates them, the parent is going to wait for all children. How? By doing pthread join. So after this, it's going to do for loop pthread join. So parent is going to wait for all children to complete their searches. Now, number 3, the parent is going to, it's not going to be waiting for all of them to terminate. It's going to be checking on the children. So it will be checking on the results, on the children results, and it will terminate under one of 2 conditions. Now, what are the 2 conditions for termination? Now, when the parent keeps checking on the results of the threads, there are 2 conditions for termination. Yes?
One of the threads finds a 0 or all the threads complete.
Yeah, exactly. Yeah, exactly. So the parent is going to keep checking on the children. If one of them finds a 0, then we know that we are done. If all of them are done, then we know that we are done. So the parent will be checking on this. But how? How will the parent know the results of the children? It will know that through global variables. So now, in this assignment, we're using global variables for communication between threads within the same process. So in this assignment, we only have one process, unlike assignment 1. In assignment 1, we had 2 processes. Here, we have one process that has a parent thread and k child threads. Okay? One parent thread and k children. Oh, now how will the parent know about the results of the children? We have some shared variables. So we have, this is the number of threads. This is the number of threads that are done. So this is a counter that indicates how many threads are done, which means that whenever a thread is done, it's going to increment this counter. So we should initialize it to 0 at the beginning. Then, whenever a thread is done, it's going to increment this counter. And there is an array of size k, the number of threads. For each thread, there is an entry in that array in which that thread should write its minimum, and it should write a boolean indicating if that thread is done or not. So the thread done array should be initialized to false before we start the search. So there is a function there that initializes shared variables, and I think I'm giving you this function. Initialize shared variables. So there is a function for initializing shared variables. What does it do? It initializes thread done to false, and it initializes the minimum to the maximum random number plus 1. And it initializes the number of done threads to 0. And of course, since we are doing this using 4 different methods, you must call this function before each method. And in fact, I'm doing this for you because in previous semesters, students used to forget to do this. So initialize shared variables should be done before starting each search so that we can have a fresh start and not get results from the previous method. So we're going to do it using 4 different methods and do the timing for each method. Okay. So now here, when the parent checks on all children, you will need to write some code for the parent to check on these shared variables and determine if a 0 has been found or all threads are complete. Now in method number 4, parent waits on a semaphore. So what the parent will do after creating the threads is just do wait on a semaphore. And this semaphore, I'm giving you the name of this semaphore, which is completed. So now the parent will just wait on the completed semaphore. Okay. So the parent will do nothing basically. It will wait on completed. So who should post completed? Well, if the parent does it, then who should be doing this?
So that's,
Yeah, one of the children. But under what condition should a child post the completed semaphore? Again, there are two conditions under which a child will post the completed semaphore. What are the conditions? Yeah.
If one of the threads finds 0, or if it notices that it's the last thread to finish.
Yeah, exactly. So if a thread finds a 0, it's going to post completed. If a thread completes and finds that it's the last thread to complete, it will post completed. Now, how will it how will it know if it's the last thread to complete?
The global variables.
Yeah, exactly. So these shared variables, by checking, for example, on this counter, the done thread count. If the done thread count, after incrementing the done thread count, if the done thread count is equal to the total number of threads, then it knows that it's the last child to complete. So the point here is that all the children will be executing the same code, right? So the code on the child side is going to be the same. But how will the child know which child it is? How will each child know? How will a child know its own number? Does a child need to know its own number? What does the child need to know? Like, you will be writing one function that all children will be executing. Now, how will the children know to search in different divisions in the array? How will it know? How will each child know? Otherwise, if you write the same code, all children will be doing the same thing. But that's not what we want. We want each child to be searching in a different division in the array. How will we do that?
When you do the pthread create, you hand it to,
Yeah, when we do pthread create, what do?
you tell it which part of the array to search.
Yeah, so we pass that through the indices array. So the indices array, I erased that because I have limited space here. Okay, so the indices array has for each thread the thread number and the start and the finish. And if you pass to each thread, if you pass to it the row that corresponds to that thread. So for thread 0, you pass row 0. For thread 1, you pass row 1, and for thread 2, you pass row 2. Then it will know its indices. So a very important piece of information that you must pass to each thread when you do pthread create is the start and end indices for that thread, so that that thread knows which division to search. And you pass that by, for pthread create, you pass a void pointer. And in this case, if you pass indices of I here you pass indices of I. Indices of I is a pointer to the ith row. So this is a valid void pointer. Indices of I is going to be a pointer to the ith row in this indices array. So basically, the code for the children is the same. Everything is the same except for the start and end, which will be parameters passed to each child. Okay? So with the parent waiting on a semaphore, the child will post the semaphore when it finds a 0 or when it completes and it finds that all other children have completed. Okay, so now, the point is, so this is not a coding exercise. So the point here is not to do the coding. So if you do the coding and it works and doesn't crash and it gives you some numbers, it doesn't mean that you have learned what this assignment is intended to teach you. The assignment is intended to teach you parallel programming, multi-threading, and synchronization. So you know that you have understood this assignment and you have achieved the learning objective of this assignment if you have a good explanation of the numbers that you get. The point here is to understand when each one of these four methods is faster and why. So let's try to think. By the way, I want you to report the results for these 6 test cases. These 6 test cases, test case number 1, array size is 100 million, number of threads is 2, the index for the 0 is 50 million plus 1. Now what's the point in 50 million plus 1? Why is it 50 million plus 1? What's the point? Yeah.
So the 0 is in the second thread?
Yeah, the 0 is in the second thread, but where in the second thread?
The first spot.
Yeah, in the beginning of the second thread. And here, 75 million plus 1, the 0 is in the beginning of the fourth thread. So if we look at this, test case number 2, we have a 0 right here. Now, why is having a 0 right in the beginning of the fourth thread an interesting test case? Why is it an interesting test case?
Is it because it completes immediately?
Yeah, because it completes immediately when you are doing multi-threading, right? If you are doing it sequentially, in the sequential, this should take a lot of time. You'll need to scan all of this until you get to the 0. So basically, this is trying to show you the difference between sequential search and parallel search. With sequential search, you'll have to scan this whole thing when there are no threads. Now, when there are 4 threads, the thread number 4 will find this immediately, right at the beginning. Now, when thread number 4 finds it at the beginning, now which of these methods is going to give the fastest time? So here, parent waits for all children. Now, in this case, when parent waits for all children, is this going to be the fastest? But is it going to be faster than sequential?
Yeah.
How much faster than sequential will this be?
3 times.
How much faster in this specific case? Is it going to be 3 times faster, 4 times faster than sequential?
4 times faster.
I think it's 3.
If we're using an RNG, isn't it possible that a 0 shows up at spot 1 anyway?
0 shows up at?
So it's possible for a 0 to show up at slot 1 with just randomly, right? So it's only potentially 3 times faster?
No, well, we put only 1 0.
Oh, okay, so
there is only one. If there is a 0, because we generate the data such that there is only 1 0 or no zeros.
Oh, so our random number starts from 1 to a...
Yeah,
to
yeah.
okay.
So random number generation is from 1 to a certain maximum,
Yeah, okay.
and then we put only 1 0.
Yeah.
So in this case, the parent waits for all children will be faster than the sequential by a factor of 3, because sequential in this case is going to search, it's going to go through 3 divisions, but parallel is going to go through all 4 divisions in parallel. So that's the key idea is, this is parallel. Parallel is just like this. You're doing this, they are all 4 divisions in parallel. While sequential, we're doing this. So this is sequential. So in parallel, one thread will be doing this, another thread doing this, another thread doing this. So the time for parallel, if there is a 0 here, is 1/3 of the time for sequential. Now if there is no 0, what will be the ratio between parallel and sequential? There is no 0. what will be the ratio in speed? If there is no 0, what will be the ratio in speed between parallel and sequential? So when there is no 0, sequential will search the whole thing, while parallel will search what? It will be effectively searching one division because it will be doing 4 divisions in parallel. So with a 0 here, parallel is 3 times faster than sequential. With no 0, parallel is 4 times faster than sequential. It's very important to understand these speed up factors and why. Yeah, question?
Does this assume a multi-core processor? Or
Well, okay, so thank you for asking this. We're implying here, what we are implying is that the processor, this is an extremely important question. We're implying that the scheduler will be able to put each one of these threads on a separate core. That's the whole point. And if these threads are going to be, if you have a single core, then you're not going to benefit from this. Remember, you're not going to benefit from dividing the array into threads. Remember when we talked about multi-threading and multiple core, we said that the operating system is not going to divide the program into threads for you, and dividing the program into threads is done to utilize a multi-core system, a multi-core processor, the multiple processors, the multiple CPUs that you have. So this is a way of utilizing a multi-core system. So we will get that if here we are assuming that we have at least 4 cores. So with 4 threads, in order to benefit from 4 threads, you should have 4 cores. Now, if you have less than 4 cores, of course, you will not get a 4x speed up. There is no way that you can get a 4x speed up if you have only 2 cores. What I'm implying here is that each thread will be put on a different core by the scheduler, and then they will be executing in parallel. And then we have a speed up factor of 4 if there is no 0, and a speed up factor of 3 if there is a 0.
so do you need us to test on a for our hard test? Do you need us to test on a machine that has at least 8 threads or 8 cores for number 3?
Yes. Well, at least 4 threads.
Okay.
Because here, there is a test case with 8 threads. It will be interesting to see how this works on a 4-core machine. So on a 4-core machine, you will not get the maximum speed up that you can get. So there will be, when you have 8 threads, there will be a huge difference between running this on an 8-core machine and running this on a 4-core machine. So on an 8-core machine, you will get the speed up that you expect. Plus, it's not going to be the ideal speed up. There will be some overhead. It's not going to be 4 exactly. In the real world, you'll get something close to 4, but not 4, because there's a lot of overhead in system overhead. As we said, there is system overhead, there is communication and synchronization overhead, and all of that. So if you expect 4, you will get 3 point something. Okay, but yes. So we want you to run this on a machine that has at least 4 cores, and that's why in your report you should report the number of cores, because the results, the numbers that you will get, will depend on how many cores you have on the machine. Right? So in particular with this, if you run it on a quad core, you will get totally different numbers than if you run it on an 8-core machine. And also, it's for when you do performance evaluation and timing, you need to run it on a dedicated machine so that we know that you are the only user on the machine and that you are not competing with other users. Okay.
What if your CPU is 4 cores and 8 threads, like it has hyper-threading? Does that change anything?
It does, but it's not like, so it's a thread will not be having 2 threads on a core, on the same core, is not exactly as powerful as having 2 two different cores, right? So it will give you some speed up, but not as much as having two different cores can give you. Okay, so let's now go back to this example with a 0 here. Then we know that this should be faster than sequential. Now, when the parent checks for on all children in this case, when the parent checks on all children, so in this case we'll need to write some code to check on the shared variable to see if a child found a 0 and if all children have completed. So should this be faster or slower than number 2?
Faster.
Yeah, faster. In this case, the parent will be checking on the children, and it will detect that this child found a 0, and then it will cancel all children. So this should be, ignoring the overhead. This should complete in 0 time, ignoring the overhead. But there is an overhead. The overhead is in the parent checking on the children and on in the system overhead, and it's not going to be ideal. Now, when the parent waits on a semaphore, so which should be faster, parent waiting on a semaphore or parent checking on children? Now, assuming that I have a 4-core machine here, a 4-core machine, and I have 4 divisions, which should be faster, parent waiting on a semaphore or parent checking on all children? Yes?
Fourth one, parent waiting on a semaphore.
Why?
Because it doesn't have to waste clock cycles checking every time. It just has to wait until it sees the completed by the semaphore.
Exactly, that's the point. So when the parent waits on a semaphore, the parent will be in which state? In the waiting state. So it will not be on the ready list. It will not be on the ready queue. So it will not be competing for CPU cycles. Now, if you have 4 cores and 4 divisions, so when you have 4 divisions plus parent, you have a total of 5 threads competing for 4 cores. So in this case, when the parent is checking on children, parent is using CPU cycles and it's competing with children for CPU cycles. Now, if you have 8 cores, you shouldn't see a significant difference between 3 and 4. Or if the number of cores is greater than or equal to the number of children plus 1, the number of cores is greater than or equal to number of children plus 1, or it's greater than or equal to the total number of threads, then there shouldn't be a significant difference between 3 and 4. Because when the parent wastes CPU cycles, it's wasting CPU cycles on a different core. It's not wasting CPU cycles, it's not competing for CPU cycles with the children. Okay. All right, so this is if we have a 0. Now, what if we have no 0? If we have no 0, then we said that parent waits for all children is going to be 4 times faster than sequential. Now, if we have no 0, which should be faster? Parent checking on children or parent waiting for all children? Well, there is no 0. Checking on children? No. Parent waiting for all children will be faster when there is no 0. Why?
Not wasting the CPU cycles again.
Yeah, but here, when it checks on the children, it will be using CPU cycles, and all of these CPU cycles that the parent will be doing for checking purposes will be wasted. Why?
Has to wait either way.
Because?
The parent has to wait either way for the children.
But why will they be wasted? They will not.
We'll never find out when the children's done until they're all done.
Yeah, because there is no zero. So it's checking, hoping that one of the children will find a zero. But if there is no zero, none of the children will find a zero. So the parent will be wasting lots of CPU cycles, hoping that a child will find a zero, but no child will find a zero. So all of those cycles will be lost. So checking on all children should be slower than waiting for all children. And you should see the difference if the number of cores is what? So the difference between this and this will be measurable if the number of cores is what?
Less than the number of threads.
Well, less than or equal to the number of children. Or if it's equal to the number of children. In fact, if it's less than the number of children, then we will not get the speed up factors that we are expecting. But if you have 4 cores and 4 children, in this case, if the parent checks on children, the parent will be thread number 5. And thread number 5 will be competing with the 4 other threads for 4 cores. So in this case, you should see a measurable difference. If you run this on a 4-core machine with 4 threads, and there is no zero, you should see a measurable difference between parent checking for on children and parent waiting for all children. Okay, so the whole point in this assignment is to think about all of these things. Again, it's not coding, it's not, your focus shouldn't be in the code. Well, you should write the code right, and the code should be functional, but when you are done with the coding, you're not done. You are done when you have an explanation for the results that you will get. Okay. Okay, I think I have covered all the issues for the assignment. Any questions? Okay, so calculate indices, and then before starting each method, you do a set time. So I'm providing you with the code that does the timing. So set time means like set the timer, and get time, it gets you the difference in system time between this point and this point, which means that this will measure the time for the code that you wrote here. Oh, by the way, one thing that I forgot to mention about the assignment 2 is that there are 2 semaphores in the assignment. There is the semaphore that the parent will be waiting on, and there is a semaphore for protecting the access to the shared variable. So there are 2 different semaphores, and each one is, each semaphore is implementing a different concept. So in this synchronization, there are 2 different purposes of semaphores. One is protecting a critical section, or protecting access to a shared variable, such that only one process or one thread is modifying the shared variable at any given point in time. And the other is doing dependence. And the completed semaphore in the assignment is one of those dependence semaphores. So it's something that you can do with semaphores, but you cannot do with locks. Unlike the protection of shared variables, you can protect a shared variable using a semaphore or a lock. But dependencies, you can implement them only using semaphores. You cannot use locks. Locks will not help.